Hello, it's Stat135, Lecture 36. This is a special online lecture because school is closed today. So last time we talked about a confidence interval for the Tyche line. In the case where we have a new observation, we can also write a confidence interval for the expectation of y given that x is that new observation. Today we're going to finish linear regression. We're going to talk about the decomposition of the total sum of squares. The total sum of squares is the residual sum of squares plus the model sum of squares. This should remind you of ANOVA. We're going to talk about the F statistic for regression. We're going to talk about R squared, the coefficient of determination, which is a generalization of the correlation coefficient squared. And we're going to talk about multiple linear regression, which will build on all that we've done. So the decomposition of the total sum of squares, this is not covered in your book, but is obviously very important. From homework number 9I, you showed essentially this equality in the case of simple linear regression. Just like in ANOVA, it says that we can divide the total variability of the dependent or response variable into two components, the variability of the regression line about the mean and the residual variation of observations about the regression line. So in a picture here, we can see that the variability of y about the mean is equal to, well actually, so the distance here is equal to, as you can see, the distance of y to y hat plus the distance from y hat to y bar. So that's total distance is the residual distance plus the model distance. The interesting thing is that the sum of squares of the total distance is the sum of the residual distances squared plus the model distances squared. So that's quite an interesting result. So in lecture 33, we showed that the residual sum of squares has n-2 degrees of freedom, and the total sum of squares has n-1 degrees of freedom. Furthermore, the residual sum of squares and the model sum of squares are independent. So that's not the easiest thing in the world to see, but let's see how that goes. So remember our geometric approach to finding b hat that we talked about in lecture 32. So we have y that is sticking outside of the column space of x, since the dimension of x, which is k plus 1 by n, is, or k plus 1 is less than n. We defined b hat to be such that it minimized the residual the residual here, the residual sum of squares, in fact. So y minus x beta hat, so it's minimize that vector, excuse me. So to minimize that vector, or actually the Euclidean norm of that vector, so for that to happen, the residuals are orthogonal to the column space of x, and hence orthogonal to y hat, which lies in the column space of x. So we know that x bar, y bar lies on the regression line. That's something you showed in homework 9. So that means that when we plug x bar into x in this formula, we get out y bar. So y bar actually lies in the column space of x, and it's orthogonal to the residual. So 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 the residual and yi minus the average are orthogonal. Now, since the joint is bivariate normal, orthogonality implies independence. So it follows that RSS and MSS are independent. Since the TSS is just n minus 1 times s squared, from lecture 34 we know that RSS over sigma squared is a chi squared n minus 2 degrees of freedom. And since y1 to yn are independent normals with variance sigma squared, it follows that the yi minus y bar over sigma is normal and is standard normal for all I, and hence by a theorem in chapter 6, the TSS over sigma squared is a chi squared with n minus 1 degrees of freedom. So it follows then that the MSS, which is the TSS minus the RSS, is a chi squared of 1 degree of freedom. Okay, so next we have F statistic for regression. This is also not in the book. We wish to test whether our predictor and response variables are independent. In other words, let's say that we want to test that beta 1 is 0. Of course, so when beta 1 is 0, then y is just y is just your intercept, your regression intercept plus an error. There's no dependence on x. So we're going to let the null be that beta 1 is 0, and the alternative is that beta 1 is not 0. So here's our picture, right? So we have our regression line here, and so our regression line, we have values y hat I for all our different n observations, right? And those, of course, lie on the regression line. And the spread of these values about y bar is bigger and the steeper that beta 1 gets. So if the null is true, then the MSS would be very small, right? Because the regression line would be very shallow. So remember from chapter 6, the definition of an F distribution. So U and V are independent chi-squares with M and N degrees of freedom respectively. Then U over M over V over N is a FMN distribution. And for us, U is MSS over sigma squared, V is RSS over sigma squared, and M and N are their respective degrees of freedom. So we get then the chi-squares just cancel out. So we get that MSS over RSS over n minus 2 is F1 n minus 2. And so how is this going to generalize? With k predictors, the 1 will become a k and the n minus 2 will become an n minus k minus 1. Just a little foreshadowing for what's to come. So we reject the null when this is large. So not surprisingly, just like in ANOVA, F is t squared. And so for simple linear regression, the F test is equivalent to a t test. So the t test for beta 1 is 0. Now, next we're going to talk about r squared, the coefficient of determination. So in homework 9.b, you showed that sigma squared E hat is 1 minus r squared sigma hat y. And so we can sort of rewrite that now as RSS is 1 minus r squared TSS. So just notice from this that since r is the correlation coefficient, that's between 0 and 1, so 1 minus r squared is less than or equal to 1 between 0 and 1. And so clearly RSS is less than TSS, but of course we knew that from our decomposition of TSS as RSS plus MSS. But anyway, R squared is 1 minus RSS over TSS, which we can also write as just MSS over TSS. So R squared becomes capital R squared in multiple regression, and it's called the coefficient of determination. So interpretation is that this is the fraction of the total variation of y explained by the model, so MSS over TSS. If MSS is very small, the slope of the regression line is small. In other words, R squared is close to 0. If MSS is TSS, the data lies essentially in a straight line. In other words, R squared is 1. So because 1 minus R squared is less than or equal to 1, RSS is smaller than TSS, as I just said. So in general, RSS decreases or remains the same as we add more predictor variables to the model, and we'll see that when we talk about multiple regression. And just an aside that ANOVA really is a special case of regression. I'm just going to talk about this informally, that essentially if you imagine your X now is your different treatment groups, so this is not going to be a continuum of values. It's discrete, treatment 1, treatment 2, treatment 3, and for each treatment we have our different Y values. Then you can fit a best fitting line through that, and that is regression. So the regression line goes through the point of averages for each group, and you can see that RSS then is SSW and MSS is SSB. So it just ties together what we've done before. So finally, multiple regression. So multiple regression, it's similar to simple linear regression. If you go back to the beginning of lecture 32, where we introduced